Problem 1 in Chapter 7 has to do or deals with estimating demand for a business based on historical information. Now the estimate we're looking for looks something like this equation here, where I'm calculating a systematic component of demand, which is the sum of the quantity of the level and the trend, and then adjusted, stretched, or compressed based on some seasonal factor. And what we need is we are somehow going to create a regression equation so that I can forecast demand. And there's a number of steps that we have to go through, and a few of them I'll go through in this video, and a few of the others I'll go through in other videos. But the first one is I have to de-seasonalize demand. So the data in problem 1 shows some seasonality. What does that even mean? Well, notice that it peaks in approximately the 11th to 12th month of every year as we go from year 1 through year 5. So peaks, sinks again, peaks, sinks, peaks, sinks. So what I'm trying to do is claim that, well, this seems to happen, these peaks seem to happen about every 12 months. That's the seasonal component. So I am trying to take that seasonal component, by the way, the bottoms too, trying to take those out as well, out of this data. So step number 1, de-seasonalize demand. Once I have that de-seasonalized demand, I will use it to run a regression, where the de-seasonalized demand will be the dependent variable, and time will be the independent variable. Once I have that regression, I will have obtained, I actually will have this level portion, the L, and the trend portion, which will be the slope of my regression. And I will use L and T in order to get estimates for all time periods. Once I have that, I can move on to calculating seasonal factors, and then I have something complete, something where I can calculate this systematic component of demand month by month. So let's get to work on de-seasonalizing demand. First thing we need to know is, well, what do we have in the data? What is it that's usable? And truly the only thing we know is what demand actually was, month by month for 5 years. So I do have that information. I have demand. I have to estimate all the other information, this level component, the estimate of trend, the seasonal component, and this forecast. And I will eventually be using this function to forecast period t plus 1 while living in period t. But the first thing I've got to do, according to my list, is de-seasonalize demand. When I look at this mess of an equation, which was on page 184 of the textbook, what can I do to make it not messy, so that it's easy to deal with, easy to function with? First off is to kind of recognize what I have. And the only way sometimes you can recognize what you have is if you start playing around with these equations. So, what values can P take? What values can T take? And what does that mean for my summations? And so on and so forth. Well, P is the periodicity of the data. And we saw that in the picture. A period is measured from peak to peak to peak to peak to peak. So the period of our data is 12 months. So P is determined. We now know what P is in this equation. Alright, what else do we know? I know this, just from experience now, I'm giving it to you so you know it. Averages compress data. It takes information from multiple points in time or multiple measurements and compresses it into a single piece of information. So this is what this is doing. This is compressing roughly 12 to 13 pieces of information. And it's doing it by averaging. So both of these expressions are averages. One I use for when the time period or the periodicity is even, like we have, 12 is an even number. And one of these calculations we use when p is odd. And notice that when p is odd, it's actually the simpler of the two expressions to look at. But how often are time periods odd? Quarterly, that's even. Annually, that's even, etc. I mean, most of the time we're going to be using this upper equation to de-seasonalize demand. Now, another big question is, because I'm compressing information, I'm going to lose data. So I won't have an estimate for d bar sub 0 because I don't have enough information to go backwards in time to beyond or before d sub 0. So here's what I got to figure out. How far back in time or how much data am I going to lose? Well, that's actually fairly easy to find out. And what I do to find that out, and you may not know this unless you play around with this equation, but this subscript on this very first demand number is the smallest subscript in the entire statement. So let's see, the first piece of information that I have is d sub 0. So the question becomes, when is t minus p over 2, wherein is t minus 6, equal to 0? And the answer is when t equals 6. So our first calculation for d bar is d bar sub 6. I can't go any further back in time because I don't have enough information to go further back in time. Similarly, when I get down to the other end of the data, in other words, when I've made all of my estimates, how far out into time can I go? So here's what I'm looking at. In this calculation, the subscript on this second element is the furthest element out into my time series. So we have 59 elements in our time series. So the question becomes, what value of t makes t plus p over 2, or t plus 6, equal to 59? And the answer is t equals 53. All right, so I know that I'm going to lose information. I'm not going to have a measure for d0, d1, d2, d3, d4, d5. I also know that I will not have a calculation for any values of t bigger than 53. So let's start working. Let's work through this calculation and figure out, well, what data points are in this first average. Well, let's see. Look at this. I've got a t minus p over 2, which we just learned that if t is 6, that this is 0. Notice that I have a t minus 6 plus 1 as the starting point in my indexing on the summation. So if this is 0, this is 1, is where it's going to start. Also notice that if t is 6, then t plus p over 2 is going to be t as 6 plus 6, so 12. Well, notice that up here in the superscript on this notation is t plus p over 2, t plus p over 2, which is 12, minus 1. So it's going to, this summation is going to start at 1 and end at 11. So I have demand element 0, 12, and 1 through 11 in the calculation of my first dt bar. Let's go over to Excel and let's put in this calculation. So this calculation says I can construct my average by taking D0, which is sitting in cell C2 and has a value of 2000, add to that D12, which is sitting in C14 and is the number 3000, and then I'm going to add, notice I've got 2 times the sum. If I have a summation notation with a constant in the inside of the summation, I can pull the constant to the outside. So I just have 2 times the sum of every number in between 2000 and 3000, or the numbers 1 in time through 11. And then I'm going to divide that by 2 times p, or 24. Now, the good thing about Excel is that it accelerates in repetition. So if I get this equation incorrectly, I should be able to calculate an estimate of d bar sub t for t from 6 all the way up to 53. Okay, so let's try this out. I just copy it. So I copy this function all the way down to t equals 53. Okay, why can't I go any further than t equals 53? 53, excuse me. Because if I do, I will run out of data. So I will start hitting zeros and not getting any contributions. So there's my calculation for the de-seasonalized demand. And notice I did lose information. I lost 6 pieces of information here, and I lost 6 pieces of information here. We go back to our steps. Next step, regress the de-seasonalized demand against time. And that is what I will do on the next video.